and we are recording. Okay, today's lecture is on YouTube quality of service, and let's go ahead and get right into it. So what we'll cover, basic measures and issues around quality of service, things like latency, jitter, and buffering, how you measure it, how you manage it. And then we'll get into some specific issues of YouTube's cloud, some of the issues about database systems, server utilization, how new users get assigned to servers, that sort of thing. Okay. So YouTube, everyone I'm sure is familiar with it. It's this on-demand streaming video site carrying a mix of copyrighted and user-generated content. It's been around for a while. It was founded in 2005 and acquired by Google shortly afterward. And it primarily earns revenue through advertising, but also uses some paywalls and subscription methods as well. So, you know, there are certain premium options that it tries to sell you. For example, the possibility that you don't have to see commercials. There's other things, some content, for example, if we go to YouTube here, let's go to YouTube, let's see what we get. All right. And if we get, let's look up, what are we checking here? We are looking for, oh yeah, Disney. So Disney, Pinocchio, okay, if you wanted to watch that, boom, from 1940, you could watch it. You had the option to buy it. It's probably gonna be like 30 bucks, 20 bucks, okay? So yeah, they sell some stuff too, right? And Disney movies are a popular source of revenue for that. Okay, and they have ads, they sell stuff on the side too. All right, so that's basically YouTube stuff. So primarily earns revenue by advertising, but also has some paywall subscription services like YouTube Red. Every few years, they try to bring out a new subscription service and generally doesn't take well, but they're still in there trying. Anyway, scale. It is a very large website. Number 3 in terms of visits, has about 5 billion video views per day and about 1 billion through mobile devices. So they get a lot of activity there. And there's probably a few billion videos in their repository. I have not been able to find a current accurate number on that. And certainly growing by a couple million, or give or take, every week. Just for me, I'm putting up a few every week. So there you go. All right. Now, what is quality of service? Well, before we get into it, let's talk about what it is. So quality of service is a term that's generally applied to networked systems and applications and roughly means how well it's working. Problem with measuring quality of service or defining it is it can mean different things at different times. But the big issues are essentially how much data the network is pushing through and how reliable it's pushing that data through, how reliably. Now, again, because of some case-specific details, it's kind of often used as a composite catch-all buzz phrase, right? So you'll hear the different telecoms saying, we provide the best quality of service. Well, again, there are many different ways to measure quality of service, right? Is your sound quality the best? Do you have the most perfect transmission of all the data you're trying to send? Does the data get there quickly? Does it get there very reliably, which is to say maybe the average speed isn't perfect, but all the packets that push through the network, they're going at approximately that speed. So depending on what you're looking at in terms of quality of service, there are a bunch of different measures, and it kind of makes it difficult to pin down. So here's an example. You have typical users using an email system, right? Well, for email, speed isn't that important. If it gets there in, you know, half a second versus 1 second versus 2 seconds, it's not that big of a deal. What is important is that the email gets there reliably, that you know that all the data that got pushed into the pipes comes out on the other side correctly, right? So email reliability is very important. Speed, not so much. Likewise, for images, in many cases, image quality is more important than speed. If you upload a photo to Facebook, you want it to be precisely the image that you uploaded. You don't want a bunch of little floating bright spots, they call them fireflies, in that image. And you would rather have it get processed a little bit slower and have the image be correct than have it processed very quickly and potentially look a little garbagey like that. On the other hand, for streaming video, speed and reliability in many cases are more important than minor data loss. So if you're watching some live streaming video of whatever it might be, and it's showing at, say, 40 frames per second, that's going to be too fast for a normal human to really process variations, minor flaws in individual frames. So the big thing for video is often that the video keeps playing continuously If that means that here and there you lose a little fragment of a frame, well, so be it. So again, quality of service for different applications, different users can mean different things. Okay, but we have it as a general idea, we mean how well the network is working. Now, specific to streaming video, if you had very high quality of service for a streaming video application, that would mean that a typical user could view it transmit it over the internet with just about as much reliability and accuracy as they did from a stored video, right? You would have it flow very quickly as if you were pulling it from RAM on your machine. Now, what is a data stream? Well, it's a set of transmissions with a specified order. And in the case of a video, you have a bunch of different frames. So if you're showing some video that's 24 frames per second, then for every 1 second of video, there's going to be 24 images that get flashed onto the screen, and probably some sort of associated audio stream as well. Now, in the data stream, each of those transmissions could be one or more video frames. They could be raw, they could be just exactly how they were originally made as images, or they could be compressed in some way. But anyway, as you're receiving that stream, right, your video application will process them and convert that data stream into actual viewable frames. Now, in the case of streaming video, once you've received all the transmissions that are associated with the video, you've received a complete string of frames from end to end, you can watch the complete video. But you need to have them all in place before you can watch the whole thing. Now, what are some key problems? Well, number one, what happens if frames arrive out of order? Well, that could mean you could wait if you're missing an early frame, you might have to wait a very long time. So you get all the later frames, but you miss an earlier one. Well, the video has to be on pause until that earlier frame arrives. Likewise, if the video is very large, you have to wait for the entire thing to arrive. That could take a while. If you're trying some 2-hour movie and you have to wait, a few minutes for it to get started because it's trying to download the whole thing, yeah, it's kind of annoying, right? You'd rather get started right away. You just say, give me enough video to get started watching it, and then bring in the rest while I am watching it. And then last questions, what if a few frames arrive very late or never arrive at all, right? You'd say, well, the whole video download process, it stalls for a while, eventually it hangs up, and then says, so sorry, I didn't get it, try again later. That would kind of suck, right? In many cases, we'd rather watch as much of the video as we can right now and not have to wait for the whole thing to arrive. So these are some basic problems with video streaming. Now, quality of service problems, what sort of problems are common there? Well, slow starts, that's one. If you're trying to watch a video, generally on YouTube, it's going to pull in some chunk of data before it gets started. And once it has enough data stored in your browser to start the video playing for like the first 15 seconds or so, then it'll get going. But it wants to get that first chunk of data first. Second, choppiness. So often you'll see that the video starts and stops while it's playing, and that's quite annoying. Okay, so nobody wants that. But again, that can often happen if your video stream gets interrupted. If for whatever reason, some other higher priority traffic pushes your video stream traffic out of the way. And last, bad quality, right? If for some reason the packets aren't coming through in their correct form, some of them are missing, some of them are corrupted, whatever, some of them arrive in low quality, then yeah, you could have your video stream start to look all pixelicious, right? There'll be a bunch of kind of bigger, chunkier rectangles on it. Now, most of these problems have the same root cause, which is too much traffic on the network. So the technical term for that is network congestion, right? If there are too many users running too many applications trying to send too much data through the network, it's analogous to a road with too many cars. Basically, first everybody has to slow down, and eventually you get something like a traffic jam. So more users running more apps and more data per app, that's all going to multiply. And those factors, again, the network can only push through so much data no matter what. There is an upper physical bound on how much data can be pushed through. And if more people than that are trying to use the network, well, somebody will have to wait. So when network traffic exceeds the system's effective capacity at any point, delays have to happen. There's no way to push through more data faster. All right, so let's give an example. Suppose you have two transmitters A and B that both want to transmit to some receiver R. Okay, so let's draw a picture of that. Okay, here's A. Let me know. Very good. Here's A, here's B, here's R, okay? And they're both trying to transmit. So A and B both transmitting to R. Okay, so if A and B both transmit at the same time, the transmissions are going to interfere with each other. Okay, so we can understand, suppose A is trying to send out, so I'm going to draw their signals here. Here's A, here's B. They're both sending out some kind of signal stream. It's going to be, you know, basically a sequence of ones and zeros. And I'm just drawing, you know, for every thing that A is sending, right? B is going to be sending some too, and sometimes they're going to overlap and sometimes not. So what will happen is if these two signal streams get received together, they're basically going to interfere with each other, right? And what the R will receive will be some kind of garbled mess that's not what A is sending and not what B is sending, but again, some kind of garbled mess. The signal streams are going to interfere with each other, and R is going to be, oh man, I cannot process this. This is a mess. Okay, so you don't really want A and B to try to transmit at the same time, because that's what happens. Now, if there is a very low utilization network, if we're saying the network isn't very busy, A and B aren't transmitting to R very often, then yeah, you might say, okay, take a chance, right? Whatever you're trying to do, whenever A wants to transmit, go for it. Try to transmit to R. Whenever B wants to transmit, fine, go for it, go to R. And if on the off chance that there is a collision, which is unlikely, then R just says, there's a collision, both of you guys stop transmitting, try again a little later, right? Again, if the network is not very busy, usually that's manageable. However, as the network starts getting busier, right, imagine if there were a whole bunch of other devices all periodically trying to transmit and all occasionally colliding with each other, right? So these transmissions are occasionally crunching into each other, right? He's trying to transmit to B, whatever. They're trying to transmit. You get the idea. These arrows look terrible, but I hope you get the idea of what's going on here. It would be like in a crowded room with 50 different conversations going on, and everybody's talking full volume, and nobody can understand anything. Okay, that would be the sort of problem that could happen, which means that the solution of saying, hey, everybody try to transmit whenever you can, and if there's a collision, we'll just try again later. If the network is busy enough, that sort of process is just not going to work very well. So what happens? Number one, interference becomes normal. Number two, network traffic is going to get dominated by retransmission attempts. That means every time somebody tries to send out a packet and it fails, they're going to want to try again later. But every time they try again later, there's a pretty good chance that that retransmission will interrupt somebody else's conversation. And so it's going to just snowball at itself. So there's going to be, number one, a backlog of packets. Number two, anything that can be transmitted will be transmitted and will cause, perpetual headaches. So in the end, what will happen is a lot of traffic will get backlogged because of all these retransmission attempts. Devices will keep trying to resend their packets. Everything will get backed up. Many packets will time out, and the communications will fail. So what you need to deal with that problem, some kind of transmission scheduling scheme, right? Basically, some kind of mechanism where the different devices agree to take turns transmitting. Now, the basic ideas between transmission scheduling, number one, transmitters don't transmit if another device is currently transmitting. That should be transmitting, not transmitted, transmitting to the same receiver. Okay, and if two devices do transmit to the same receiver, they incur a random delay before transmitting again. Okay, so this is what's called the binary exponential backoff scheme. Is one of the more widely used. I'm going to roll it back to our original, just A and B and R case. Okay, so A and B essentially, they agree to take turns. They agree to follow the rules and not just try to transmit whenever they can. So what's going to happen? A and B are going to listen. Okay, they're going to listen to the network, and if they sense that another device is transmitting to R, they're going to wait. They're going to say, "Oh, B is talking to R. don't be rude, I'm going to give B a chance to finish before I jump in and send my packet to R. Okay? And there's generally going to be some kind of slightly random delay before transmitting again. And the more time, with binary exponential backoff, which is the standard approach, A is going to wait twice as long following each interruption. So if A has, a random delay that starts out being about 1 millisecond, it's going to listen to see if B is done. If B isn't done, it's going to check back again 2 milliseconds later. If B is still, or somebody else is still transmitting to R, A is going to listen and come back in about 4 milliseconds, and so on. So basically, the delays tend to double in one of the more common schemes. Now, however, there are many, many different scheduling schemes. This is not a computer science course. This is just IDS 200, so we don't actually need to know what these scheduling schemes are. But there are different ways you can optimize them for things like minimum average delays. So how long a device has to wait before it gets a turn to transmit. Number 2, minimizing the risk of interference, right? So that can be an issue in remote networks where power consumption is an issue. Basically, you don't want devices to transmit if their power is going to be wasted. And last, ensuring equal participation by users. Basically, having some mechanism in place to make sure that everyone eventually gets a turn to transmit. Okay, so again, transmission scheduling schemes are basically a way of having devices take turns transmitting so that you can have an orderly regulation of traffic in the network. Just like cars on the road, they follow the signs, they follow the traffic signals. Yeah, same kind of idea. Okay, so with that, let's get into some of these issues with video problems and where they come from. So the first one is latency. Latency is simply transmission delays, and it can happen at the source of the data or intermediate nodes on the routing path, so nodes, devices, hardware devices that the packets go through. Now, all transmissions are going to have some latency because the electrons that are going through the cables, they don't teleport, right? They're really fast, but they don't teleport. Even fiber optic signals, right? The photons going through, they don't teleport. They move at the speed of light, which is super fast, but they don't teleport. So in practice, what you see is about 1 millisecond of delay per 100 miles traveled. Okay, obviously that is much slower than the speed of light, but there's a lot of electrons involved too. So what this, again, in practice, that means if you're trying to talk to a server on the other side of the world, like 10,000 miles away, yeah, you're probably looking at about 1/10 of a second delay, right? So 100 milliseconds for 10,000 miles. And in some applications, that can be noticeable. Of course, if the network is busy, right, if you're trying to do anything on a server where there are a bunch of users, then yeah, network congestion can have it be even longer. And we see this all the time, right? So if you have tried some new popular online game and it's running on some servers, but the servers are really busy and everything feels kind of slow and sludgy and laggy, you're like, yeah, this is what's going on. There's too many people trying to do things at this server. It's congested. You got to wait a little bit. So everyone, I think latency makes a lot of intuitive sense. People can understand that, again, if the network is busy, somebody's going to have to wait. Okay. The next one, jitter. Jitter is a little bit more difficult to understand. So I'm going to draw a picture for that. So imagine we have 2 machines, 2 servers, 2 clients. Okay, and it's going, whoop, I don't know why it always does that. It's annoying. Okay. And it's going through some device here. So we'll call this client A. You can be, and we'll have server S and server T over here. Okay. And let's describe the problem. So client A is watching videos from server S. Okay, this is considered a low priority stream. Okay, so for whatever reason, client A's traffic is considered less important than client B is doing something else T and is considered a high priority stream. Okay, don't need to know what client B is doing, but whenever client B contacts server T, he gets priority, right? So whatever server T does, that goes to the top of the stack. So the way this is going to play out, let's suppose each of these cables has a 1 gigabit per second capacity. Okay, all cables have a 1 gigabit per second capacity. So suppose most of the time client A typically needs, say, 0.5 gigabits per second for his traffic stream. Okay, client B not continuous, but when B needs it, B needs about 0.8 gigabits per second. Okay, so remember, B is high priority. Whenever B shows up, B gets what B wants. So most of the time, there's plenty of capacity for A to S, right? So for A to get the data from S, there's plenty of capacity. The cables are all 1 gigabit per second. A only needs half of that. But when B shows up, B takes a big chunk of the capacity, leaving only 0.2 gigabits per second for A, which means A will experience intermittent slowdowns. Okay, and there's not really much that A can do about this. It's just going to happen. So this is a way that jitter can happen. Let's talk about what jitter is. Jitter is simply the variability in the delay of transmissions. And in some cases, if transmissions are following multiple paths, it can even make the packets that are sent arrive out of order. Now, like latency, some jitter is inevitable, right? The hardware isn't perfectly synchronized. And especially if packets are being routed over separate parallel paths, then yeah, there could be some time differences there. But jitter often becomes severe when congestion affects a subset of transmissions. That is, in our example here, as long as client A is the only one using the system, everything's fine. But whenever B shows up, A is going to feel that, right? A is going to suddenly notice, oh, you know, it used to be great, but now it's not so great. Now I'm only getting like 40% of what I need. And if B is on there for a long time, A is going to experience that as a long, you know, unpleasant delay. If B just pops in and out, right, just says, oh, quick note to server T and back, and then pops in, you know, like a minute later and gets another thing, A is going to notice that as occasional slowdowns. So this is where jitter comes from, is generally you have multiple users with different priority levels, and some, you know, one device is getting high priority and the others are getting less priority. So the lower priority ones, they experience that as jitter. Of course, it can happen in other ways too. It can also happen, you know, if you occasionally have multiple users and some of them are doing different things at the time, right? So imagine if A and B both using applications of equal priority, but on occasion A is running like 10 of those applications while B is maybe running 1 or 2. So if A is trying to run 10, yeah, number one, A is going to notice that things slow down for him, but B is also going to notice because A is going to start trying to take a bigger chunk of the data, right, of the data transmission capacity. So jitter can happen in various ways, but essentially it just means some packets are going to be delayed, others aren't, and you'll experience that as basically a jerky, slow, fast traffic flow. Last one, packet loss. So in packet loss, some transmissions don't arrive at all. Well, what happens? Let's talk about how that works. So suppose what we have here, this is a switch with some available memory to store incoming packets, right? So as packets arrive at the switch, this is strange. Okay, as packets arrive at the switch, some of them will be stored in memory, okay, if it can't immediately do this. So ideally, the switch would immediately forward on any incoming packets. Okay, but if it's receiving packets faster than it can send them out, then some will have to be temporarily stored. Okay, so example here, suppose A is running two applications. A is simultaneously receiving data S and receiving data from T. Okay, so we're doing that at the same time. And each of these, say, requires 0.8 gigabits per second. So there's enough capacity, right, to handle this traffic going through. He can handle 1 gigabit per second and send it to the switch. T can handle 1 gigabit per second and send to the switch. But the switch downstream to A can only push through 0.8. So what that means is unless S and T are deliberately regulating how fast they're sending the data to the switch, it's going to build up, right? There's going to be more data coming in through these 2 gigs per second of capacity than can be sent out on the other side. So eventually what can happen, if the backlog is sustained and severe enough, eventually the delay will be long enough that it gets handled like a system failure, right? We basically say, yeah, we tried to handle this packet, we held on to it for a while, but it's been down long enough that, you know, maybe it's being held for 5 or 10 seconds or longer. And at some point we decide, you know what, we're going to treat this as basically a hardware failure, and we're just gonna chuck that packet out of the switch, right? Because what happens, even if you don't do that, eventually the switch memory gets overloaded anyway, right? Memory is finite. If you keep having packets come in, eventually the switch memory is going to get overloaded, and then the next packet that comes in, it'll either have to throw that one away or it's going to push something else out of the switch's memory. So again, that's how packet loss can sometimes happen. If you're trying to do too much stuff and there are delays in the system, yeah, these switches in between devices do have memory, routers can have memory, but at some point that memory is going to be overloaded and not be able to handle all the backlog. Okay, so what you should know, what latency is, how it arises, what jitter is, how it arises, what packet loss is, how it arises. Okay? All right. Questions on any of that? This is a good little bit of a break point to talk about some stuff. Any comments, questions, thoughts, concerns? Nope. All right. Moving on. So the next thing to talk about is buffering. So video streaming applications use a technique called buffering to help smooth out the traffic flow and thus deal with latency and jitter. So in essence, what it's doing, the application is going to build up a reserve of data, typically several seconds or even a minute or more. And that way, if there are any interruptions in the data flow, the application will still have available some reserve of video play time. Now, if you have a longer buffer, you have naturally more reliable operation. In an extreme case, if you downloaded the entire video before playing it, basically you would have the full buffered video and you could watch the whole thing regardless of what happened with your network operation. But if you have a shorter buffer, that means you could start playing sooner, right? Because the more buffer you need to have to start playing, that's going to delay when the video can actually start. When the video can start playing. So, for example, let's go to YouTube. Let's see what we get here. We got parakeets. Okay. So we got this. We're going to watch some parakeets for a minute. Okay, now if you look here, you can see where the video is, but you can also see that little gray bar right around here that shows how much of a buffer there is. So right now we've already loaded like a few minutes worth of data, right? So this is an hour or so video, and we have a little bit of about a minute worth of data already loaded up there. So if I wanted to, I could just jump ahead, right? I could jump ahead to there, and the video keeps playing. All right, that is one happy bird there. Okay, and if I wait a little while, you'll see the buffer keeps on going, can keep on going. It can even try to buffer a little more, but YouTube doesn't really want to buffer all the time, right? It could, so you can see it creeping up very slowly there, but it's really going to take its time doing it. YouTube's not going to bust its ass trying to download the whole video for me when it doesn't know if I'm even going to stick around to watch it. But again, it'll keep that buffer going. So again, you can see there, you know, it creeps up a little bit there, and it's trying to keep up so that if anything goes wrong, it can keep playing continuously. Now what I can do here, I can temporarily disconnect my wireless. So boom. And now I'm back. And even though I lost connection for a bit, right, the video kept on playing. So that's the magic of buffering. Okay. So basic issues that get addressed. Number one, if there is any sudden latency, that's going to be handled until latency extends past the buffer's end, right? So if I have a 15-second reserve of video data and latency is 10 seconds, I'm never going to notice that latency. The video is going to keep on playing, right? I have enough reserve built in that the video can keep playing continuously, even though each packet takes 10 seconds to arrive. Likewise, jitter gets handled. So if there are some individual packets that take 10 seconds to arrive, but I have a continuous 15-second reserve of data, again, I'm never going to notice that jitter. It's going to keep playing continuously, even though some of those individual packets might take a little while to arrive. Even lost packets, even some packet that gets dropped by a switch somewhere in the routing process, even there, if it can be recovered and resent in time, as long as I haven't exhausted the buffer, I would never notice that packets were lost. So buffering, basically, you have a certain amount of video data stored so that you can keep playing it continuously, even if you have some sort of connection or quality of service problems. Okay. Now, like we said, quality of service metrics are a little tricky because it does mean different things to different users of different applications, right? So it's not a single monolithic variable. It's not really meaningful to say our network has great quality of service unless, you know, it genuinely does have great metrics on every possible thing that might be involved in quality of service. However, for simplicity of understanding and as a marketing tool, it's often represented as one. For example, if you wanted to get a rough code of how well the system was working, you might have green for quality of service really high on most metrics, or red for it's bad on one or more metrics. But still, it's more correct to present quality of service as a set of metrics, including things like latency, jitter, packet throughput, how many packets you're pushing through the system, that sort of thing. So this is basically the objective approach, right? So we can say quality of service, if it meets this defined standard, we have good quality of service, right? So you have some objective that you target, and if you meet it, that's great. But you can also consider it subjectively, which is to say, are the system's users happy with the quality of service? If so, you can say that the quality of service is good enough, right? Because in the end, what matters is how well the users feel it's working. So if performance meets some operating standard like a service level agreement, or if the user satisfaction levels are high, then yeah, your quality of service is good enough. And of course, for different applications, it'll be different. You'll accept a lot more delay in an email application, for example, than you would in a voice over internet application. Okay. Now, more about quality of service measurement. We have a concept called peak to average ratios. So peak to average ratio is basically the ratio between peak traffic and the average traffic. So if your system has a flow that looks something like this, right? Basically a daily cycle that looks something like this, that maybe it's quiet during the day, it peaks up a little bit in the morning, right? Then it peaks a little bit, and then it comes back down. Okay, whoop, didn't want that. Then it comes back down at lunchtime, and then maybe it goes back up again in the evening. And then stays busy for a while. And then, damn it, it was harder than it looks. Okay, and then it has a rapid fall off at the end of the day, something like that. Okay, this could be a reasonable pattern. So the average might be something like this, right? This could be your average. Let's bump that up a little bit. But the peak, of course, is about twice. This is your average, and this is, of course, the peak. So roughly, peak to average ratio is about 2, right? If I've drawn this proportionally and all that. Okay, so the bigger your peaks are relative to your average traffic, that's going to create problems, because in order to meet this peak demand, you're going to have a lot of hardware available that's going to be idle most of the day, right? So if I have enough traffic, if I have enough hardware to say meet this green line, right, to number one, not only handle the peak but have a little bit of safety margin on top of that, well, guess what? Most of the time, right, all this time roughly around here, this is going to be pretty much idle most of the day, right? This is money that I've spent on hardware that most of the day I don't need. That's a big problem, right? That's spending a lot on hardware that I'm not using. It's analogous to, okay, I'm going to buy a big house because one day out of the year I have a birthday party where I invite 50 people over. But the other 364 days of the year, it's just me and the dog. Anyway. So that's the kind of problem that real networks have to deal with. So many networks experience significant but transient bursts of heavy traffic. That is, their network is busy for a little while every day, but not for the whole day. Now, when those bursts happen, you can get drops in quality of service because the network gets busy, right? So for example, if instead of that much, suppose your network said, well, we can't really afford that much. We'll have enough to handle, you know, our morning peak, but for the rest of the day, yeah, you know what, it's just going to be a little bit slow over here, and we're going to live with that. And it's going to be a much cheaper thing because even though we don't have quite enough hardware on hand to meet that peak demand, well, guess what? Most of the rest of the day we do, and our, you know, more of the equipment that we have is actually being used throughout the day. So that's you know, that's basically a cost-based decision. But if you want to have your network be robust, that means it can survive trauma, essentially, you would try to manage peak demand rather than the average demand, right? So what will happen in practice is people will see that, oh, this kind of sucks at this time. They'll go use some other comparable service that's not busy. This, in fact, actually often happened back during the 90s. So when the internet was a new thing, what we often saw with America Online, AOL, America Online, was very, very busy around 6 to 9 p.m. every weekday evening because people came home from work and wanted to do internet stuff, okay? And that's what I was, and AOL just didn't have enough capacity. So people would literally try to call and recall to log into the network, because we used dial-up back then, right? We were glad to have it, to log into the network. And it could take 20 or 30 minutes. And that's how it was, and it kind of sucked. So by the time broadband rolled around, when broadband became an option, many people were very glad to get there. Okay, so, and AOL lost a lot of market share. Now, towards the late 90s, yeah, AOL fixed this mostly. The delays were not nearly so bad, but still, you know, this was unpleasant. Eventually, if your model is controlling costs by saying, yeah, sometimes our network is going to be really busy, that's not good long term. That's not going to make people happy. Okay. So anyway, when quality of service goes awry, when you have a shortfall, you can ask some basic questions. Things like, number one, how many users are affected? So you might say, well, we've identified that what's really causing this surge in traffic is that we have a small number of very heavy users, right? We have a few people that are doing, say, a lot of live video streaming, and it's putting a big load on our network. So you might say, let's throttle those users, or we'll say if that's a non-critical application, we'll throttle that non-critical application, and yeah, we'll affect a few users, but you know, we'll affect a few users to make a lot of other users happy. We could also add things like what portion of network traffic is affected. If it is a very brief transient surge, like literally lasts a few seconds, yeah, maybe that's something you just live with, right? You say if we have these transient, very short transient bursts where, you know, peak to average ratio is like 10 or 20, yeah, it might not be worth having that much capacity under your roof to deal with it. It might actually be a better, much more sensible option to just, you know, accept that on occasion there's going to be a few seconds delay. Likewise, what fraction of the day is affected? If it lasts for a long time versus lasts for a short time, you know, same issue there. But these two in particular tend to be correlated, right? The longer portion of the day that gets affected tends to mean that more traffic is going to be affected. In general, if many users are affected, then yeah, that's also going to represent a large share of network traffic. So these answers tend to be correlated, but in some ways they can be different. For example, you can have a very short burst that generates a tremendous amount of traffic, right? For example, if everybody arrives in the door precisely at 8 in the morning and they all turn on their computers at that same time and they all got to connect to the internal servers and get data, and it's all trying to do it within a few seconds window, yeah, that could be a big hassle. It could involve quite a bit of network traffic, but only lasts for a short portion of the day. In practice, what you would probably want to do is find some way to, you know, stagger the access so that not everybody is trying to do it at precisely the same instant. Anyway, but these are all case-specific details. Okay. Now, video quality, right? So ideally, a streaming video application would receive every frame in time to be shown. Ideally, the quality of service is good enough so that as soon as the time for one frame to be done happens, the next frame is available and ready to be seen. But interesting thing, for human viewers, different delivery problems are perceived differently. For example, typical humans are only going to be able to notice somewhere around 25, 30 frames per second. If your frame rate is higher than that, you might not even notice occasional missing frames or portions of frames. But if it's real live streaming video, latency and jitter, those are definitely going to be noticed if they exceed the buffering capacity, right? So if you have a long latency delay, like or some jitter that results in packets being received like 20 seconds later, but your buffering is only 10 seconds, yeah, that's going to make your video start and stop and seem choppy, and people just say, oh, this is awful. Now, interesting thing, YouTube primarily doesn't use what's arguably the more technically perfect option. So we'll talk about this. TCP and UDP. So the two big models for communication are TCP, which stands for Transmission Control Protocol, and UDP, which stands for User Datagram Protocol. They're both ways of pushing data through networks. Now, TCP is connection-based. What that means, all right, I'm going to draw a little map here. I'm going to draw a little network map. And a few devices in the middle, whatever. So this is going to be the source. This is going to be the destination. And these are going to be some intermediate devices. Whatever. Worried about how the things get there. Okay, but we recognize that there's Is that everybody? Yeah, I suppose. Okay, we recognize that there are different paths to get places in the network. I'm going to do one more. I'm going to do. Okay, so fine. So there's some network that these packets are going through. Now, with TCP, what's going to happen is that the network builds the path. So first, TCP network builds a stable routing path and sends every packet in order over that path. Okay, so for example, I might say go from here to here, here to here, here to here, and here to here, right? And then every packet in that communication is going to follow that same routing path. So when we say TCP is connection based, that's what we mean. We create a stable, persistent path for sending data. So creates a source destination path allowing for data to arrive in the proper sequence. Because every time I send off a packet, I'm going to keep following up the next one right after it. Each one is going to arrive in order at each step of the process, each step of the path, and they're all going to arrive at the destination in order. Also, TCP provides guarantees about packet delivery. Okay, so with TCP, if any intermediate node doesn't get a packet, the sender will try to resend it. Okay, so the essential idea there, the guarantee is not that a packet will definitely get there. The guarantee is every time the source sends a packet to say the next step will return a confirmation says, thanks, I got it. And then the source knows it's time to send the next one. So if the source doesn't hear back from this guy after a while, then it's going to assume, oh, that packet didn't get through, I'd better resend it, right? But, okay, so let's add, but the resend process, I'll say what's called a handshake, and resending process slows things down. Okay? So if I'm waiting for that confirmation, that's going to take a little time. That's what's called the handshake. And if I have to resend it again, I have to wait for that timeout to happen before I do send it again. And that makes things happen a little slower. UDP, on the other hand, let's use orange. UDP is fire and forget. Okay, so any packet might get sent down a different path. So I might send first one, it gets there this way based on the local situation. I say, oh, maybe this is the best path. And maybe I send another one and it goes, you know, a slightly different path, right? Maybe it goes to here, to here, to there. Maybe there's a lot of other data on this transmission. And then I send another one, it could take a totally different path, okay? So with UDP, number one, no guarantee of arrival sequence, okay, because they could be, each packet in a communication could be sent down a different path, so there's no guarantee they're all going to arrive, you know, in sequence. Number two, when we say it's fire and forget, there's no handshakes or confirmation, and no resends. Now, of course, your applications can choose to resend data. If at the end of the day they found, oh, I didn't get all the data I need, then you can ask for a resend. But UDP doesn't have resends built into the model. Okay. So the nice thing about UDP, again, because no handshakes and resends, data tends to arrive faster, right? So when I say UDP is arguably more technically perfect, this is what I mean. It tends to push more data through the system faster. However, it's also less reliable because no guarantees of recovery from delivery failure. Okay, if a packet doesn't get through, TCP will try to resend it. UDP will say, well, didn't get through. You knew what you signed up for. That was a foreseeable risk. Okay. So TCP is connection-based. UDP is connectionless. It does not build a single stable path between the source and destination. And in particular, lost packets are not sent again. Now, performance comparison, again, TCP is slower than UDP. TCP gets slowed down because receivers acknowledge every packet that gets received in order to prevent them from being retransmitted. UDP, on the other hand, is less reliable than TCP. A packet that gets lost stays lost. UDP isn't going to try to resend it. Now, true real-time streaming often uses UDP because users aren't going to rewind the video anyway. So if a packet doesn't get through, oh well, it didn't get through, that's life. Which conceptually is like listening to the radio, right? You get into the car, you flip on the radio, it turns out that they're just wrapping up the last 10 seconds of your favorite song, and you say, oh man, I wish I had a rewind button, but I don't. Okay, so UDP is like that. And of course, this is also applicable to real-time video games. If you're trying to play some real-time game, you don't want your network connection getting clogged up with data that would have been useful 10 seconds ago, right? You're just like, well, that moment is gone. I didn't get the data then, but it's of no particular use to me now. It's just going to slow things down. So in some cases, UDP actually makes a lot of sense, right? If data gets lost, well, it's just lost. It just didn't get through, and we'll recover in the next update. However, YouTube generally uses TCP for a couple reasons. Number one, YouTube isn't true real-time streaming anyway. What it actually does is it takes a video, chops it up into segments, and feeds you one segment at a time. So it's actually like multiple sequential file downloads. It's not true streaming. It doesn't deliver each packet to you as it happens. The other issue, number two, some systems can block UDP because it's hard to tell if packets are responses or part of some kind of denial of service attack. So with TCP, the way it works, you send out a request to a server, and your device says, I would like to receive such and such data from you, and that goes through your firewall, and your firewall says, oh, you initiated a request to this server, so when that server sends a stream of data back to you, it's not at all surprising that you're getting the stream of data. And in particular, the packets arrive sequentially, so your firewall can look at that and say, ah, yeah, okay, this makes sense, all the packets are arriving correctly. However, if you're using UDP, number one, all of those packets can be arriving from different intermediate points. So that's one problem that makes it tricky for firewalls to identify them. Even if they all say they're from the same server, the firewall can't really clearly verify that they are. It's just to say, well, these packets are marked as if they are. So it's going to be more cautious. Number two, if packets arrive out of sequence, again, the firewall is going to be a little bit more cautious about that. It's going to look and say, hey, this is weird. This is a packet that arrived out of sequence. Doesn't really make sense. I am concerned about this. I might not let this packet through. So again, some firewalls in particular do block UDP because it's difficult to detect if incoming packets of data are actually part of a stream that you expected or just somebody trying to screw up your system. So that's essentially why YouTube started off with TCP, because if they'd gone with UDP, they figured that about half of the firewalls in the world would have blocked UDP, and they would have lost a lot of business opportunities that way. Okay. However, Google has been working on something called the QUIC protocol. And essentially what it does is it tries to be about as fast as UDP and about as reliable as TCP. So essentially, it's UDP with multiple parallel streams that are checked for reliability. But still, it's a little different. It's kind of weird. So there's some reliability checks built in. And it's used by YouTube for some traffic. It's also used internally by a lot of Google systems. And eventually, there'll probably be some similar protocols down the line that are probably going to become widespread for a lot of real-time applications. So essentially, here's the comparison. TCP has handshakes for individual packets, and those packets are received in a single stream. What QUIC does is it sets up parallel delivery sequences. So UDP, remember, if a packet fails, if it's lost, it's just lost. Well, what that can do for UDP is it can essentially invalidate the whole data delivery process. What QUIC does is it sets up multiple parallel delivery sequences. Each of those, right, keeps sending data out. If one of them pauses while it's waiting for data to arrive, the other several of them can continue. So the idea is the whole pile of data will get sent at UDP speeds, but there's a mechanism built into it for recovery. If at the end of one of those parallel delivery sequences they recognize, oh, we didn't get all the data we need, then QUIC is going to try to relaunch that delivery. So that's the idea there. And the hope generally is that only doing that for some of them instead of all of them like TCP, you get most of the speed advantage of UDP, but you also get the reliability of TCP in that if a stream fails, or a substream fails, resent. I should also add, for any systems that block UDP or otherwise incompatible, QUIC will automatically revert to TCP. So that's built into the protocol that if there's a system that just looks at UDP and says, nope, no thanks, not dealing with this, then QUIC is just going to say, yeah, okay, we'll use TCP for you. Okay, so again, UDP and TCP, they are not the last word in these things. Technology, in a variety of ways, is always being updated. Okay, let's look at our time. We want to talk about Dash. Let's leave Dash for another day. I feel like this is a good break point. We covered pretty good chunk. Okay, questions on any of this stuff? Anything at all? What about live stream videos on? Yeah, well, if they are live stream, they're probably using QUIC, or they probably want to, if they're genuinely live. I mean, we could do a quick Google on that. YouTube live stream QUIC. Let's see what they say. YouTube, yeah. I'm going to say if it's true live stream video, chances are it's QUIC, but YouTube has the option to do it in different ways. Okay. Anything else? I mean, I guess even if they're using QUIC, right? If it's a system where it's on the viewer, if the viewer is going to block UDP, then you're going to see it as TCP anyway. But if it's true live stream, then YouTube's not going to store it and segment it and do all that. It's going to send it live as it happens. And UDP is probably better for that. Yep. Anything else? All right. Oh, one question that was wrong. Oh no, you're right. I gotta add that in. I did not do that. Thanks for reminding me. Yeah, I'll do that. So all exam grades should be +5 points. That'll happen later today. Okay, I'll do it right now. I had a couple people that were waiting to take the exam through Sunday, so I didn't actually post the grades, and yeah, that needs to happen. Yep, no problem. And hopefully I will get other thing for extra credit. Hopefully I hear back from, what's her name, Rashana this week, and can post those grades. Okay, so, but once I get the list of participants from her, I can put that in the system as well. All right, well, that's all I got then. I suppose